Now let's define fiber bundle by an example, and then we generalize it in more general case. If we take an example as a curve, as a manifold, which is one-dimensional manifold, and all the tangent spaces associated with it, at each point there is tangent vector associated with this manifold, then the tangent spaces with the TB with the manifold form what's so-called fiber bundle. And now we will discover its importance and its properties as well. First of all, we will use convention in order to make the image more easy to imagine. And so instead of taking tangent vector at each point, we will represent the tangent spaces as parallel line passing through the associated point of the manifold. For example, at A there is this dashed line, at B there is parallel dashed line of the one of A, and so on. This is bundle, fiber bundle, but this is very special one. We will see why, because here we can define what's so-called projection. That means at each point of the tangent spaces we can find map that associated this point with the associated point of the manifold in M, and we call this map as pi, for example. But this pi doesn't necessarily exist in more general case. So this is one thing. And here we have all the degree. We restricted ourselves to talk about the tangent spaces, and this is also make the example more particular, because in general case we can take any spaces associated with each point, which doesn't necessarily be tangent, the tangent spaces, any spaces, and we can form fiber bundle. And we will see a very interesting example at the end why this structure is very important. Here, natural question could be raised. What is the dimension of this fiber bundle? First of all, or before that, this fiber bundle form new manifold. New manifold. So I take base manifold, I take spaces associated with each point, I form a new type of manifold called fiber bundle. As we see that the manifold, the base manifold M is one-dimensional, it's curved. So the dimension of M equal 1. But what is the dimension of Tm, which is tangent bundle? To respond at that question, we need to find coordinate system, a good coordinate system. And we explained previously what this between brackets could means. If we take the interval A and B in figure B, the interval between C and D in figure B, and we can choose an index X, and one index is enough to define, we make a map with R1, and it's enough to parameterize this interval in a good way. But also in this new manifold, in this new structure, I need another index in order to parameterize the tangent vector associated with each point in this interval. So any tangent vector in this interval could be written as y, let's call it v, is written as v equal y d over dx, where y is the component of this tangent vector. So I need another index which is y. So I need two indexes to parameterize this new manifold. So this new manifold, this new fiber bundle has dimension of 1 plus 1 equal 2. We can generalize it in more general cases, where is the fiber, the associated tangent, the associated field the associated space is more arbitrary. For example, of degree m dimensional fiber, and with manifold with n dimension, the formed fiber bundle will have the dimension of the sum of the two dimensions. So n plus m. And here finally we will give some example. The previous example is what so-called tangent bundle, which is very special case, as we explained previously in the first. Also, when we talk about a vector field, we can naturally generalize any vector field to tensor field. So the tensor field is natural generalization of vector field. So for any dimension manifold, the differential manifold M, there is corresponding tensor field where we can form new fiber bundle. But in this case, it will be more complicated structure, but also we have more degree of freedom to characterize, to use them as characterize for characterizing. As an old example of fiber bundle is the Newtonian absolute space. In Newtonian absolute space, where time is absolute for every one, we can use the space which is Euclidean of degree 3 as a manifold, and we can associate vector field as a time. This structure called we can form a fiber bundle. But this is this is Newtonian Galilean structure where the order of any two events is the same, no matter where this event happens, and this is corresponding to Newtonian point of view of the world. But here is finally the most interesting example, which is more, we can say, relativistic time space. We can take time space as a manifold, okay, as a manifold time space, the relativistic time space as a manifold, and we can imagine, for example, isospin particle. Isospin particle at each moment has a spin state, so we can choose the space of spin state as a fiber. So this structure formed by time space manifold with the space of spin state as a fiber also form a very interesting fiber bundle, where at each point of the trajectory of this isospin particle, I can know exactly where is it and exactly when, and also the spin state of it